Have you ever stopped to think about what holds our world together? I mean, beyond gravity. I'm talking about the tiny, totally invisible forces that decide if something is a solid, a liquid, or a gas. Well, today, we're diving into the story of that invisible glue and how one person's understanding of it actually solved a major medical crisis. You see, for a huge part of human history, leprosy was just this devastating disease. It wasn't just the physical symptoms, it was the intense social isolation it caused. And for the longest time, the best shot at a treatment came from a very specific kind of oil. But there was a problem. This so-called treatment, it was flawed, it was painful, and honestly, a lot of the time, it just didn't work. It took the incredible mind of a young chemist to figure out how to unlock its true potential. And in doing so, she gave all of us a perfect real-world lesson in the fundamental forces of chemistry. So who was this chemist? Her name was Alice Ball. And back in the early 20th century, she was faced with a very, very sticky problem. Literally. Okay, so the potential treatment came from an oil from the chalmugra tree, but it had this massive physical issue. The oil was extremely viscous, which is just the scientific way of saying it was super thick, and it really resisted flowing. Think about trying to inject something as thick as molasses. It just wasn't working. So Alice Ball's huge challenge was this. How do you change the oil's physical properties without totally wrecking its medicinal ones? And she had this incredible insight. She realized the key wasn't just about the molecules in the oil, but about the forces between those molecules. She had to somehow loosen that invisible glue that was making the oil so thick. And that, right there, is the core of what we're talking about today. We are talking about something called intermolecular forces. These are the attractions that basically tell molecules how they should interact with each other. So what even are these forces, really? Because, they aren't the super strong bonds that hold a molecule itself together. There's something else, something subtler. Okay, here's the deal. An intermolecular force is an attraction between separate molecules. A great way to think about it is, you know how water molecules stick together to form a droplet? That's them. That's the force. It is the invisible glue that holds liquids and solids together. And this right here is a super important distinction to get. Intramolecular forces, like the covalent bonds inside a water molecule, those are the super strong connections within a single molecule. They determine what a substance is. H2O is water because of those bonds. But intermolecular forces are the much weaker attractions between different molecules. They don't define what it is, but they determine its physical properties, like its boiling point, or in Alice Ball's case, its viscosity. Now, it's not a one-size-fits-all situation. These forces aren't all the same strength. They actually exist on a spectrum, from these really fleeting, weak attractions to some surprisingly strong connections. So, first up, at the weakest end of the spectrum, you've got London dispersion forces. Now, these are the most universal force out there. Literally every single atom and molecule has them. They happen because electrons are always zipping around, and for a split second, you get a temporary lopsidedness that creates a tiny, brief attraction to a neighbor. Think of it like a fleeting glance between two people in a crowded room. It's fast, it's weak, but it's there. Stepping up in strength, we get dipole-dipole attractions. Now, these only happen in what we call polar molecules, molecules that have a permanently positive end and a permanently negative end. And just like with magnets, the positive end of one molecule is drawn to the negative end of another. This is way more intentional than that fleeting glance. This is more like a firm handshake. It's stronger and it's much more stable. And finally, we have the heavyweight champion of them all, the hydrogen bond. This is a special, supercharged type of dipole-dipole force. It only happens when a hydrogen atom is bonded to one of just three elements: nitrogen, oxygen, or fluorine. Water is the classic example here. This isn't a glance, it's not a handshake. This is a strong, lasting hug between molecules. So this really sums it all up, right? You've got the weak but everywhere dispersion forces, the medium-strength dipole-dipole forces for polar molecules, and then the really strong hydrogen bonds in those special cases. And it's simple. The stronger the forces, the more those molecules are going to want to stick together. And this brings us right back to Alice Ball's sticky problem. The chalmugra oil was just packed with these big, bulky molecules with strong intermolecular forces, which made them cling to each other super tightly. That high attraction led to high viscosity. The genius of her solution was that by chemically tweaking the molecules, she was able to weaken those intermolecular forces, which made the oil finally thin enough to flow easily. But here's the thing. These forces do so much more than just determine how thick an oil is. They are basically the master architects of the physical states of matter itself: solid, liquid, and gas. Every single time a substance changes state, melting, freezing, boiling, you name it, what's really happening is a battle between energy and these intermolecular forces. Think about it. To melt ice, you have to add heat energy to start overcoming those hydrogen bonds that lock the water molecules in place. To boil water into steam, you need even more energy to break them apart completely so they can fly off as a gas. All 6 of these transitions are just about making or breaking those molecular connections. So, with all these changes, depending on things like temperature and pressure, you might be wondering, is there a way to map this all out? Well, yes. Yes, there is. It's called a phase diagram, and it's basically a map for matter. It tells you exactly what state, solid, liquid, or gas, a substance will be in at any combination of temperature and pressure. And there are a couple of really weird, really fascinating spots on this map. First, there's the triple point. This is one specific precise condition where solid, liquid, and gas all exist at the exact same time in perfect balance. And then there's the critical point. If you crank the temperature and pressure past this point, the difference between liquid and gas just vanishes. It becomes this strange hybrid state called a supercritical fluid. Okay, for one last example of how these forces create order, let's just zoom in for a second on the solid state. Because even when something is solid, those intermolecular forces can build things in different ways. In crystalline solids like salt or diamond, the forces lock every particle into a perfect, repeating, organized grid. That strict organization is why they have a very sharp, precise melting point. But in amorphous solids like glass or plastic, the particles are just frozen in a random jumble. There's no long-range order, which is why they get soft and gradually melt over a range of temperatures, instead of all at once. And this all brings us right back to where we began. Alice Ball's groundbreaking work, which became known as the Ball method, was the best treatment available for leprosy for decades. It was a massive triumph, not just for medicine, but for fundamental chemistry. Simply by understanding that invisible glue between molecules, she was able to engineer a life-saving solution. Her story is just this brilliant illustration of how these fundamental, invisible forces are responsible for pretty much everything we see and touch around us, from the way a medicine works to the structure of a diamond. It really shows that by understanding the very, very small, we can achieve some incredibly big things. And that just leaves one question, right? What are we going to build with that knowledge next?